In this video, I'm going to describe the Cauchy interlacing theorem that basically gives a relationship between the eigenvalues of a matrix and its submatrices. So in here, all of these matrices are Hermitian. Let's just keep this in mind. So therefore, all the eigenvalues are real. So that's one of the requirements in here. So what's a submatrix? A submatrix is essentially is obtained from a matrix by dropping some of the rows and the corresponding columns. So as a result, we always get a square matrix. So for example, if I eliminate the last row in here, and so therefore I also eliminate the last column, in that case, what is left in here, so that block is going to be the 4x4 submatrix of A. So crucial thing in here is, of course, you eliminate the corresponding rows and columns. So as a result, if I eliminated the second row, then I should eliminate the second column. So as a result, only in that way, of course, the remaining elements, the remaining matrix would be a Hermitian matrix still. Okay. So instead of eliminating one row and one column, we can eliminate 3 rows, for example. Let's say it like this. The second, fourth, and fifth. So therefore, the second, fourth, and fifth columns are also eliminated. In that case, these 4 elements, the remaining 4 elements, would be a 2x2 submatrix of A. So Cauchy interlacing theorem basically says that the eigenvalues of the submatrix is somehow lies between the eigenvalues of A, but in a we can make it a precise statement actually. So this is actually a general submatrix. For a general submatrix, the theorem is general for a general submatrix. But I'm just going to look at the case where only one row and column are eliminated. So that's basically the statement of the theorem. A is a n by n Hermitian matrix. I'm going to call the eigenvalues as lambda 1 to lambda n. So there are n eigenvalues. I also want them ordered. So as a result, they are ordered from increasing in the increasing direction. So there might be some degeneracies. There's no problem with the degeneracies. And then we eliminate one of the rows and the corresponding column. And so as a result, we obtain an n-1 by n-1 Hermitian matrix. And since this is of lower dimension, there's actually the number of eigenvalues is equal to n-1. All right. So let's just call the eigenvalues as mu1 to mu n-1. In that case, it says that all of these eigenvalues of the submatrix actually lie between 2 succeeding eigenvalues of A. So as a result, mu1 lies between lambda 1 and lambda 2, and mu2 lies between lambda 2 and lambda 3, and so on. So the last eigenvalue of submatrix lies between the largest 2 eigenvalues of A. So there's a very nice interlacing structure, and that's why we call this as the interlacing theorem. So somehow the eigenvalues of the submatrix lie between them. So this is for the special case of the submatrix of size m-1 by, submatrix obtained by eliminating one row and column. We can then generalize this to an arbitrary submatrix. So I'm going to do it at the end, but let's just discuss that particular relationship. So basically, I can assume that I eliminated the last row. So there are actually things that we can do, like change the places of rows and columns. This is actually some kind of a similarity transformation with a permutation. So as a result, I can always assume that I eliminated the last row. So the remaining, this block is the B matrix. I can also do a similarity transformation like this. Let's say it like this. I can multiply A by a matrix in the form like this, where there's an m-1 by m-1 block in here, and then zeros in here, and then there's a block of 1 in here, and it's inverse. Okay, that's essentially equivalent to taking the similarity transformation of the B matrix, and so these things are also going to change in this kind of a similarity transformation. But we know that in a similarity transformation, the eigenvalues do not change. But these kind of things will basically simplify the way of we think about the proof of the theorem. So as a result, I'm going to assume that I have done this. So I somehow do a similarity transformation and work with with a form such that the matrix B, the submatrix, is already diagonal. All right. So let me show it in here with this highlighter. So this is the submatrix B. I didn't show this 0 entries. I'm assuming that it's already diagonal and the entries are ordered like that. I cannot simplify this relationship further than this. So this is still the column that's eliminated, and that's the row that's eliminated in this process. So as a result, in that case, I then try to compute the eigenvalues of A. I cannot solve this problem, but we can say something about the eigenvalues. And of course, the thing that you can do is basically to compute the characteristic polynomial of A, basically just compute this thing. Okay. So if you do this, I'm not going to show the steps, but if you do this, you can show that this is in this form. So first we have these, let me use the highlighter in here. So we have this basically the characteristic polynomial of B multiplied with lambda minus A is basically the product of the contributions coming from the diagonal entries. That's one exceptional term. And then we have terms like for each C coefficient in here, there are n minus 1 such coefficients. For each C coefficient in here, I have more or less the characteristic polynomial of B, except that one eigenvalue is missing in there. So there are actually products of n minus 2 such terms in here. So as a result, for example, for the term I have in here, which is C1 squared, lambda minus mu1 is missing in here. So we have just the product of lambda minus 2 up until lambda minus the last eigenvalue. Right, that's one term. The second term is this in C2. I again have the characteristic polynomial of B, but again, mu2 eigenvalue doesn't appear in that expression, etc. So you can show that this is the case like that. So I'm not going to write down all the terms in here. If you want, you can also write down the characteristic polynomial of A like that. This is kind of a strange expression because we have 1 over lambda minus mu I kind of terms in here, but just keep in mind that this is actually a polynomial. So that means this is the characteristic polynomial of B. So there are these lambda minus mu i's all appearing in here. So as a result, if lambda is set equal to one of the eigenvalues, this term diverges, but there's this 0 coming in here. So if you multiply them, you're going to get a finite value. All right, so that's the expression that you may want to use if you want, but that's not always the easiest. Now, using this expression or the previous expression in here, this expression, you can actually compute the value of the PA, the characteristic polynomial of A, at the eigenvalues of B, right? So that's what I'm going to do. So when you do this, you are going to notice that it's only one term is going to survive. So you set the eigenvalue to, if you set the argument of the polynomial as at mu I, that's what you're going to get. I'm sorry about it. Let me just think about this. Yeah, that's true. That's true. So this A term, this just disappears. We have zeros coming from a lot of terms. Only one term survives, but just notice the structure in here. I'm subtracting from mu I all the possible eigenvalues except itself. So there's a missing term in here. and the product of all the other things. So you can see that in here, all of these terms are positive up until in here, because I have ordered the eigenvalues. And after that point, all of the eigenvalues are negative. There's also a minus sign in front. So from here you can see that these numbers are alternating in sign. So I'm going to start with mu n minus 1. This is the largest argument. Probably I made a mistake in here, so that should be mu n minus 1. Sorry. So if you just compute this, you're going to see that this is negative. Okay. And if you compute the second largest when you set the argument of the polynomial to the second largest eigenvalue, you get a positive sign, and so on. So these signs are basically alternating. So they have alternating signs. So the value of the polynomial at one eigenvalue is opposite to the value of the eigenvalue. Let me just show it like this. Right? We have some kind of a axis in here. I'm plotting the polynomial for the characteristic polynomial of lambda. They have some roots in here, but I'm not going to write these roots in here. I'm here marking the eigenvalues of B. So that's a different matrix, right? Mu n minus 1. So what we are saying is that this polynomial in here, let me show this with a yellow color with a thick line. So at this largest eigenvalue, this polynomial is negative. Sorry about this. Let me show a little bit more in here. This is mu n minus 2, mu n minus 3, and so on. Okay. So what I have said is this. Right. Whatever that polynomial is, I know that it is negative at when the argument is mu n minus 1, and it is positive at mu n minus 2, and it is negative at mu n minus 3, and so on. I don't know what happens in here, so there's some kind of an ordering in here. So the argument is, let's say, negative in here and positive in here. So probably I'm plotting the case where n is a negative integer. N is an odd integer. I'm sorry about that. In any case, I also know that the leading term of that polynomial is positive. So as a result, when lambda goes to infinity, this is going to be diverging to infinity. So from here, you can see that when I connect these regions, there's a point in here bigger than mu n minus 1, where this curve intersects the axis. Okay, so let me quickly do this connection. So as a result, there will be some kind of an thing in here. So this polynomial is going to change sign a lot. And so as a result, what we have in here is that I'm also going to mark these with blue color. So the blue dots represent the eigenvalues of A. So we have an eigenvalue of A in here. That's basically the largest eigenvalue. I have another eigenvalue in here. That's the next largest, and so on. Lambda n minus 2. And so on. So up until this one in here, lambda 1. And that's lambda 2. All right. So all of the eigenvalues are the zeros of that polynomial. So you can see that each of the eigenvalue of B, this one, lies between two eigenvalues of two succeeding eigenvalues of A, basically. So here I have shown only the case where the lambda i's do not have any degeneracy. So all of the roots are simple roots. But you can easily extend this argument to the cases where there is a degeneracy. So let's go back to this original statement of the theorem. So these signs are actually not strict inequalities. They can be equal or greater, for example. They can also be equal. So if it is possible, if it is the case that, for example, lambda 1 is equal to lambda 2, let's say. In that case, mu1 has to be necessarily equal to these eigenvalues. So the statement is still correct. Okay, so then this is the Cauchy interlacing theorem. Let me just, I think I'm going to go to the last page and then add a page. All right, so as a result, we have this kind of illustration. So what if k rows and columns are dropped? In that case, you use the theorem step by step, k times actually. So as a result, then we still have this. Again, let's see it like this. Lambda 1, lambda n are eigenvalues of A, and mu1 to mu n minus k are the eigenvalues of the submatrix. Okay, so in that case, lambda 1 is less than or equal to mu1. You can just show this yourself. So that's basically lambda 1 plus k. And the second eigenvalue of the submatrix is greater than lambda 2 and less than or equal to lambda 2 plus k, and so on. What was the largest eigenvalue? Mu n minus k. So mu n minus k is greater than or equal to lambda n minus k and less than or equal to lambda n. So let me shift this a little bit. I couldn't do this. In any case, I mean, this is a very simple application of the rule. You just somehow step by step consider all the submatrices that are obtained by eliminating just one row and the corresponding column, and then from here we can then reach to any step in here. So I'm not interested in this part of the inequalities in here. What's important for me is the first part. So this basically tells you that the minimum eigenvalue of the submatrix is greater than the minimum eigenvalue of the real matrix, and the second minimum eigenvalue is greater than the second submatrix, and so on. Okay, so that's n minus k greater than lambda n minus k. That's the part that I'm really interested in, because in the case of quantum mechanics, for example, the original Hilbert space is infinite dimensional, so you can think of the real Hamiltonian as an infinite by infinite matrix. So in this elimination process, you just eliminate infinite rows and infinite columns, and at the end you obtain a finite column in here. So the process is something like this. So let's say it like this. We have this Hamiltonian operator. Is usually is in the differential operator form, but doesn't matter what it is. So I'm going to call the eigenvalues as E1, I'm going to call the eigenvalues E sub n, but I'm also going to assume that they are ordered in increasing order. So therefore we have this sequence in here. E1 is the ground state, E2 is the first excited state, and so on. But we can think of this Hamiltonian as an infinite by infinite matrix too. In any case, what I do is I just eliminate some of the rows so that we get only a finite number of rows. So the formal way of doing this is like this. So let phi 1, phi 2, ... let me call phi m be a set of orthonormal states or orthonormal wave functions. Okay. We define hij as the matrix element, so that's phi I h phi j. So let's just remember that this is obtained by the usual procedure that we are all familiar with in quantum mechanics. Right? That's this integral. It's not that important, of course. So from this H, you basically get a matrix. If you just order all of these matrix elements, I get a matrix like that, HMM, HM1. In any case, I get some kind of this is an M by M matrix. Oh, sorry. Matrix. Okay, what I am claiming is that this matrix is a submatrix of that Hamiltonian operator. Why? The reason is this. This is an orthonormal set of wave functions, but it's not a basis because, of course, our vector space is infinite dimensional. But there's some kind of a theorem that says that if I have a set of orthonormal vectors, I can still add additional vectors to that list. So let's say it like this. I already have m wave functions which are orthonormal to each other. I can add new functions to that list, and still we have a bigger list, but all of the functions are still orthonormal. So this is orthonormal. And then I can complete this to a basis. In this case, when I construct this matrix in here, I don't know what to call this, let's call it H tilde, from all possible matrix elements, but in that case, of course, this is going to go to infinity. So let me just write a few of these. So this is infinite by infinite matrix. So the H tilde is an infinite by infinite matrix. Sorry about that. Let me think about it. So this H tilde, of course, is somehow equivalent, as an operator, is equivalent to the differential operator H. So therefore, this differential operator and this H tilde have the same eigenvalues. Eigenvalues. All right? When I say that this differential operator, the Hamiltonian operator, is infinite by infinite matrix, that's essentially what I mean. And then we have this procedure in here where we have a submatrix in here. We basically take this M by M block in here in the upper part. That's essentially, let me erase all of this, the matrix that we have written down. So that's the matrix H that I have written down in here. So therefore, this H is a submatrix of this H tilde. All right, so therefore I can then apply this interlacing theorem, but in that case I cannot use this part in here because K in here is infinite, so that part is not useful, but this part is useful. Right? So I'm just going to write down the this form in here. So I'm going to call this like that. So let eigenvalues of H be called epsilon n, but of course there are only m of them because this is an m by m matrix. So I also order the eigenvalues of H. Then by Cauchy interlacing theorem, the real energy eigenvalue of the real Hamiltonian is less than or equal to epsilon 1. The real first excited state energy is less than or equal to the first excited state energy of the submatrix, and so on, up until the mth one, the last one. Right? So this then tells us that the if I obtain a matrix like that, a matrix Hamiltonian, then the eigenvalues of this matrix ordered like that forms an upper bound to the real energy eigenvalues of the corresponding level. We usually think of this as an approximation because we use these kind of matrices only for approximate calculations. So these are the meanings of the approximate eigenvalues, right? Eigenvalues of that approximate matrix. So these eigenvalues somehow form an upper bound to the real eigenvalues. So what's the significance of that? Well, the significance is that sometimes there were these orbitals in here. Yeah, these ones, I choose them. Sometimes we choose them in a particularly better way. So sometimes we guess something, we guess some of the wave functions, and we think that they are actually better suited for describing what's going on there in physically. In which case, the eigenvalues of the submatrix that we are going to obtain, these epsilon i's, will be very close to the real energy eigenvalues. Right? So basically I can make these eigenvalues to be smaller. In that case, they are going to approach to the real eigenvalues. So as a result, we are going to get better approximations. Okay, so for this reason, these are actually important. And so as a result, for example, I don't know, let's say the excitation energies, these are the ones that are directly observable in experiments. If you do this kind of an approximation, then you can kind of say that if your results are actually very close, then you can also expect that the energy differences between levels that you have obtained is more or less close to the real energy differences. So this is actually some kind of a controlled approximation. So for this reason, this is important. Now, you might have heard this. The first of these inequalities is actually called the variational theorem. So variational theorem. In some quantum mechanics textbooks, of course, this is explained clearly because this is a very important tool. We just write down some kind of a variational wave function, and the expectation value of the Hamiltonian in there somehow provides an upper bound for the real ground state energy. And by using this tool, we can solve a lot of problems in a very nice approximate way. But you can see that this theorem actually says more, right? It's not just the ground state energy. Energies are ordered. The first excited state energies or the nth excited state energies, they are also ordered like that. So as a result, this somehow forms a mathematical basis for using submatrices like that to describe real physical systems. So of course, for molecules and things like that, this is usually what people are doing. Okay, so this is the next thing that I'm going to describe. This is essentially called the linear combination of atomic orbitals, but there is a slight complication in there. I'm just going to describe that complication.